5B, Newton's laws of motion. 5.4, Imagining Inertia. Scientists in the Middle Ages, relying on Aristotle's explanations for the natural phenomena, believed that all things would slow to a stop if left to themselves. This idea seems logical enough. If the engine in your car stops, your car rolls to a standstill. If you shove a book across the table, it slides to a stop. But experiments proved that models relying only on reason failed to explain everything about the causes of motion. The physicist Galileo is the first person known to have investigated these ideas. He spent a great deal of time experimenting by rolling balls down inclined planes, measuring projectile motion, and timing pendulums. From his experiments, Galileo concluded that objects continue moving indefinitely unless some external influence affects their motion. He was able to infer this, even though he couldn't directly observe such a situation on Earth. Johannes Kepler, 1571-1630, first gave this property of matter a name: inertia. Early scientists, including Galileo, never settled on an explanation for how forces cause changes in motion. One reason for this was the lack of necessary technology. To study motion, you must be able to measure time intervals accurately. Although Galileo developed several methods to subdivide time for his work, it wasn't until a few years after Galileo's death that the invention of accurate and precise pendulum clocks solved this problem. This new technology allowed Isaac Newton to build on Galileo's concept of inertia. The results of this important work were his three laws of motion. 5.5 Newton's first law, the law of inertia. Newton merged Galileo's principle of inertia into a more general statement of physics that included his own discoveries about the actions of forces. Newton's first law, or law of inertia, states, "Objects at rest remain at rest, and objects in motion continue in a straight line at a constant velocity, speed, and direction, unless acted upon by a net external force." We can't measure inertia directly, and so it has no units associated with it. Physicists quantify inertia by mass. In fact, the concept of mass was invented by physicists as measure of inertia. Newton's first law of motion defines the conditions for zero net force on a system. Recall from section 5A that a zero net force means that all forces on the system are balanced. As long as this condition exists, no change to a system's motion will occur. The system is in mechanical equilibrium. For example, a car driver maintains a constant speed by balancing the slowing forces of friction, air resistance, and gravity on hills with the driving force of the engine. The driver adjusts engine force by changing the position of the gas pedal. Newton's genius was his ability to conceive an idea that is totally outside of common experience. This law is not easy to prove here on Earth. All kinds of familiar motions are subject to two ever-present forces: friction and gravity. When you kick a soccer ball, it doesn't sail away in a straight line. It curves gracefully toward the ground because of gravity. Only deep space probes seem to be nearly free of the external forces. But even at interstellar distances, the sun's weak gravity and even the gravity of the galaxy itself can affect the motion of these distant objects. Thus, any combination of unbalanced contact or field forces acting on a system can result in a change in motion. You will learn more about friction and gravity later in this chapter. 5.6 Newton's second law, the law of accelerated motion. A small, lightweight car takes relatively little force to accelerate. Such cars have small engines that use very little fuel. Large, heavy sport utility vehicles need much bigger and more powerful engines. The larger vehicles have more mass, so they have more inertia. Newton's most significant accomplishment in developing his three laws of motion was relating the quantities force, mass, and acceleration in an equation that always works, at least in normal, everyday experience. His law of accelerated motion says the acceleration of a system is directly proportional to the net force acting on the system and is inversely proportional to its mass. Thus, a net force on an object of a given mass results in a certain acceleration of the object. If you double the net force on the object, you double its acceleration. On the other hand, if the original net force acts on another object with twice the mass, it results in only half the acceleration. Newton originally thought of his law in the form of this equation: acceleration of system, Dorshaw net force on system, over mass of system. Physicists usually write Newton's second law in symbols as F nourish m times AIE, which is simpler to remember. In this equation, F is the net external force on a system in newtons, m is the mass of the system in kilograms, and A is the acceleration of the system in meters per second per second. Newton's first law defines mechanical equilibrium by showing that what happens when there is no net force on a system. No change in motion occurs. Newton's second law shows how the motion of a system changes when the net force acting on it is not zero. 5.7. Newton's third law, the law of action-reaction. Unlike Newton's second law, we can't easily express the law of action-reaction as an equation. We can state Newton's third law of motion in these words. For every force exerted on a system by its surroundings, the system exerts an equal but opposite force on its surroundings. If you push a box across the floor, it moves because the box exerts a force on your hands. If it didn't, your hands would pass right through the box. The resistance of the box on your hands is actually the box pushing back on you. If the third law weren't true, changes of motion would be impossible because no force could act on a system. If things didn't exert forces on other things, the material universe could not exist. Particles of matter must exert forces on each other to hold matter together. Newton's third law of motion is often called the action-reaction principle. However, this title suggests that some change of motion, a reaction, always results from a force, an action. But this isn't the case every time. For example, when you push against a wall, the wall pushes against you. No motion results unless you push so hard that you fling yourself backward, or you punch a hole in the wall. Let's look at the Earth and the Moon. The Earth system exerts a gravitational force on the Moon system. This external force keeps the Moon in orbit around the Earth. You now know that, because of Newton's third law, the Moon also exerts a gravitational force on the Earth. It has the same magnitude as the Earth's force, but it's in the opposite direction. See Figure 5.12. This force causes ocean tides and movements in the Earth's crust. Newton's third law also applies in the case of a rope attached to a rock climber. The downward weight of the climber is exactly supported by the upward tension in the rope, which is the third law re-T force to the climber's weight. Figure 5-13. 5.8. Friction. Friction is everywhere and affects all motion here on Earth, slowing things down and wearing parts out. So what is friction? Friction is a contact force that works against the movement of systems past each other. You can think of systems more broadly here. Not only are they objects touching or rubbing along surfaces, such as a pencil on paper, but they are also fluids flowing around or against a rigid object, such as a current flowing around a buoy in a river channel. The direction of friction force acting on a system of interest is opposite to its direction of motion through its surroundings. If you slide a box down a ramp off the back of a truck, the ramp exerts a friction force acting up the ramp. The magnitude of friction between solid objects is proportional to the force holding the two objects together. In most familiar cases, this force depends on the weight of the object and the angle of the surface it rests on. For instance, the friction on the box just mentioned decreases if the angle of the ramp is increased. The box slides more easily. Analyzing the factors that affect friction and drag can be complicated, so we will only summarize them here. These factors generally apply to friction between solids. Some also apply to fluid drag, which is affected by other factors applicable only to fluids. Friction always occurs between systems in contact. Friction depends on the kinds of materials in contact, but not on the size of the areas in contact. Friction acts on the system of interest opposite to the direction of motion relative to the system causing the friction. The amount of friction is proportional to the force holding the two systems in contact together. The friction between two stationary objects, a box resting on the floor, is greater than the friction between the same two objects when they are sliding past each other. Physicists recognize several different kinds of friction. They include static friction, or friction between stationary objects, kinetic friction, or friction between sliding objects, rolling friction, or friction between a rolling object and a stationary surface, and fluid friction, or the drag of a liquid or gas exerted on a moving object immersed in the fluid.